Hello, everyone. Finally, I'm recovered. I can do a session, and yeah. So let's jump into some electrostatics, and yeah, I believe you can hear me well. Uh, if you can't. I have slightly unstable internet, so I'll tend not to use the camera today and just use the whiteboard. So it's going to be a different whiteboard today for the same reason, for the low bandwidth reason. Okay, so I'm going to stop my camera and start sharing the whiteboard. So share whiteboard. Oh, that's the wrong one. Okay, nope. So let me go back. More. Zoom has two whiteboards, and it's very non-intuitive. Okay. Okay, so today's topic is electrostatics, and we start with the Coulomb's law. Coulomb's law says that, just on a side note, Coulomb's law. Okay. Coulomb's law says that if you have two charged particles, let's say, or two positive particles, it doesn't matter what the charge is, and they will be repelling with a force F, and this one. If the distance between the particles is d, and well, let's make it r, because I'll tend to use r instead of d. Okay, and the charge on the one particle is plus q1. The charge on the second particle is plus q2. Okay. Right, and the force is K, where K is the Coulomb's constant, Q1, Q2 divided by R squared. This is how you typically write it in A levels, but we tend to write it like this: 1 over 4 pi epsilon 0, where epsilon 0 is a constant, is called the permittivity of free space, Q2 over R squared. So K is the Coulomb's constant. Coulomb's constant, and but epsilon 0, which is, let me constant 32 is 8.85 times 10 to the minus 12. And embarrassingly, I don't remember the units, but yeah, apologies for that. I don't remember the units for the permittivity of free space. I could work them out, but I don't want to spend too much time on this. Okay, so a good exercise actually is to work out the units for the permittivity of free space from the Coulomb's law equation. Now, this is the force between two charged particles in space. So any two particles, and as you can see, this is the inverse square law. So if you double the distance between particles, the force becomes 4 times less because it's r squared. Now, we have to define a quantity called the electric field strength. Electric field strength. And the electric field strength, by definition, E is a vector quantity, is the force experienced by a unit charge placed into the field. So how does that work? Suppose we have a field. Let's say this field is produced by charge Q capital. There's a field around the charge. And we place another charge, a very small charge, Q0, into that field. This charge experiences a force, and this force is in that way. That's the force. And the electric field, by definition, is the force per unit charge. Per charge. But we already know from the Coulomb's law, we know that the force is 1 over 4 pi epsilon 0 multiplied by Q0, Q capital. It's the Q1 times Q2, but Q1 is Q big and Q2 is Q small, divided by r squared, where r is the distance from the big charge. If you sub that in, you will see that Q0 goes away, and we have simply Q capital over 4 pi epsilon naught r squared. Now, it is a vector, but of course this is the magnitude of that vector. Okay, so I'll just add these because I don't want to add any vectors into this equation. It's not really important. You can always work out the direction by looking at the charges. And this is called the electric field strength. The electric field strength is measured in newtons per coulomb. Is measured in newtons per coulomb. So it shows you how much force would be experienced by 1 coulomb of charge. And 1 coulomb is a very big charge. Therefore, the electric field strength is usually quite a big number. So a typical value would be like 50,000 newtons per coulomb. That means if you place 1 coulomb of charge into that field, it will experience 50,000 newtons of force. It's not such a strong field. It's just a coulomb is a very massive charge. Okay, nice. So let's move on. To understand how big a coulomb is, you just calculate the force. So let's do a quick side note. Find find the force of between two charges, between two charges, 1 Coulomb each, 1 meter apart. So a very reasonable thing to find, right? And the force, so it's going to be 1 over 4 pi epsilon naught multiplied by Q1, which is 1, multiplied by 1, divided by 1 squared. So we simply need to find 1 over 4 pi epsilon naught. So 1 over 4 pi and epsilon naught. I have a calculator which has epsilon naught stored in it, which is very convenient. And you get something like 8.98 times 10, 333 to the 9 newtons. So it's a 9 billion newtons. So you can imagine how massive a charge of 1 Coulomb is, because if you just have 2 coulombs 1 meter apart, there's a force equivalent to, I don't know, what's the most powerful jet engine? Is it the G9X? Is that the most powerful? It has 80 tons, 80,000, 800,000 newtons of thrust. And this is 1,000. This is like 1,000 of the most powerful jet engines ever produced. Okay, so you can understand it's a massive force. Okay. All right. So problem one. Problem one is almost identical. Well, it's almost identical to one of the problem 3, I think, from the assignment. So you have a square with corners A, B, C, and D. So I can draw a square, and that's going to be A, B, C, and D. And we need to find the electric field at point D. So find the electric field at point D. And we have a charge at A, which is 2 millicoulombs. At B, that's -9, -9 millicoulombs. And at C is 6 millicoulombs. And okay. So first that we need to know is the principle of superposition. The total field at a point is the vector sum of individual fields. That means that the total field at point D is the sum of the field from charge A plus the field produced by charge B and plus the field produced by charge C. So we just need to find these charges. So we know that this is 20 centimeters. So we can draw. So this is a positive charge. That means it will produce a field in a downwards direction, and that would be EA. Now EC is also positive, so it's to the left, and it's triple that of EA. So that's EC. And finally, there's a third field, which is EB. Now it's the biggest charge, but it's also the biggest distance. So it's actually going to be, we don't need to know that at the moment, but it's going to be slightly less than EC actually, interestingly. And let's call this EB. It's in the opposite direction because it's a negative charge. So a negative charge produces a field towards itself, and the positive charge produces a field away from itself. So we've got three fields. We just need to calculate them. So EA, we know it's the charge divided by charge at A, divided by 4 pi epsilon naught times r squared, which is the distance. So QA is 2 times 10 to the minus 3 coulombs divided by 4 pi epsilon naught r squared, which is 0.2 squared. So let's calculate that. So that's 0.002 divided by 4 pi epsilon naught multiplied by 0.2 squared. Okay, that's 4.49 times 10. 1, 2, 3, 1, 2, 3, 8. 8 newtons per coulomb. So you see, even 2 millicoulombs produces an absolutely massive field. Like, well, massive in terms of numbers. Okay. Now EC, it's easier to calculate, but we already know it's going to be 3 times. Let's confirm that. So it's going to be QC. So that's going to be 6 times 10 to the minus 3 divided by 4 pi epsilon naught multiplied by 0.2 squared. And indeed, if you times that by 3, you get 1.35 times 10 to the 9 newtons per coulomb. And finally, EB. So EB, we need to calculate the distance first. And what's 9 times 10 to the minus 3. By the way, I'm not sure I'm seeing the chat because I haven't seen any messages in the chat so far. Can somebody just type something? So just make sure that I can see. Perfect. Yes, I can see that. Divided by, so I'm not missing any questions. Epsilon 0. Now, the distance is the diagonal of a square, so it's the square root times 0.2. So 0.2 square root of 2 squared. So just times 2. And so we can do this by 9, 4 pi epsilon 0, or 2 and times 2. And that would be 1.01 times 10 to the 9. And as I said, yes, it's going to be slightly less than EB. Just because even though the charge is bigger, but the distance is bigger as well. Okay. And now we just need to work out the total vector. So what do we have? We have a vector like this, which is 1.35. I'm going to drop the 10 to the 9, so I don't really need that. I have a downwards vector of 1.01. And I've got this vector, which is at 45 degrees. 45 degrees, and that is 1. Oh, sorry. What am I doing? No, that's a mistake. So the downwards vector is 0.45. 0.45, and this one is 1.01, and it's because it's 10 to the -9, we can say it's nanonewtons per coulomb. So that's nanonewtons per coulomb, nanonewtons per coulomb. Okay, being creative here, just to avoiding the powers. Now here, I'm going to split this into components. I'm going to split this vector into components and saying, okay, so that is 101 times divided by root 2. 101 divided by root 2. So that's 0.714. 714. 0.714. And then we kind of forget about this one, and now we find the total. 0.714 minus 0.45, that is the resultant upwards is 0.264, and the resultant to the left is going to be 1.35 minus 0.714, 0.636. Therefore, the resultant electric field, ED, is going to be square root of 0.264 squared plus 0.636 squared. So that would be squared square root of answer squared plus 0.264 squared. That's going to be 0.689 nanonewtons per coulomb, and the direction theta would be arctan of 264 divided by 636. I multiplied by 1,000 just to not to deal with decimals. So arctan 264 divided by 636, which is 22.5 degrees. 22.5 degrees. Interestingly, it's exactly, well, almost exactly half of 45 degrees. I don't know if that's a coincidence or not. But okay, that's the resultant field, or you can say it's 6.89 times 10 to the 8 newtons per Coulomb. In the direction 25 degrees, and you can say it's north of west, if you want to be, about it. Yeah, sorry, there was a message in the chat, but I did not see it. Could you please repeat that? I only see the messages when they pop up for some reason. Can you just copy the message and just send it again? Okay, I still don't see it. Anyways, so yeah, now talking about problem 2. Consider a thin, infinitely long wire which is uniformly positively charged with linear charge density lambda. Find the electric field at a distance a away from the wire. So this is from the assignment. It's actually solved in, well, there's a link to solve in the assignment. But let me just walk you through how you would even approach this. So you have a long wire, and lambda is the charge density, is the charge per unit length. So lambda is charge per unit length. And that means that the charge is lambda, the charge density, multiplied by L. So if you take a section of a wire, for example, if you take this section of the wire and it has a length L, then the charge on that section is lambda L. Okay. And you're a distance A away from the wire, so let's say you are at point P. Okay. Now, the first thing I'd like you to notice that imagine we have two sections. Like section 1, it's charged, it's positively charged, and section 2, and it's also positively charged. Both of these produce an electric field. This is electric field from charge 1, and part 2 is closer to P, so it's producing a slightly stronger field, E2. But let's consider the mirror images of 2 and 1. So let's call it 3 and 4. Now 3 produces a field which is similar to E1, E3, and E4 produces a field like this, E4. So if we can notice that the horizontal component of E1, so if we split E1 into components, and we split E3 into components, you would see that this component cancels with this component. So we only need to consider the vertical component of the field. Does that make sense? Please ask me a question if it doesn't. Because the wire is infinitely long, if some part of the wire produces a horizontal component, there is a symmetrical piece of wire which produces a horizontal component in the opposite direction. And that means that the two horizontal components have to cancel out. So we only consider the vertical component of the field. Okay. So moving down. Imagine now that we break the wire into many different components, different sections, very short sections. To know the field at point P, but we only need the vertical component. Okay, so let's say that this is the x-axis. This is 0 on the x-axis. And let's take a section of the wire which has a length of dl. Would I want to call it dl? Why not dx? That would make more sense. dx. dx is this length of the wire, and this length is you know what? I don't think I should do it this way. Let me take a section here. We take a section of the wire of length dx, a distance x away from 0, from the, yes, so it's distance x. Now the field produced would be like this, E. This is E. And we need to split it into components. We need to split it into vertical and horizontal components. So this is the vertical component, and this is the horizontal component. And we already know that the horizontal component cancels out, so that doesn't make any difference. So we only need EY, and this is EX. Now EY is going to be equal to, and so this is distance A, this is distance X. Oh, we can say that this angle is theta. So this angle is also theta. So EY is E cos theta. And now theta is cosine theta. Well, from this triangle over here, cosine theta is actually E multiplied by, well, let's leave it. Let's leave it as cos theta. Let's see where that takes us. Okay, now I want to find E. And E is small e. The field, let's call it E. is a small piece. E is the small, is now Q, as we already know, Q is lambda times dx. Q is lambda dx. And r squared, well, r squared is actually a squared plus x squared. So it's 4 pi epsilon naught a squared plus x squared. Okay, and multiplying this by cosine theta. So the field, the vertical field from this small section of the wire is equal to lambda multiplied by cos. Okay, so I have to do cos anyways. For question 1, why does EB cancel out? No, EB does not cancel out. Why? Uh, uh, I've split EB into components, into two components, and then I found the total vertical and total horizontal component, and you can see that this minus this is this, and this minus this is this. So I just found the total horizontal and total vertical component. I hope that makes sense. Okay. So yes, lambda dx. So cosine theta. Okay, I have to do cosine theta anyway. So let's do this. EI multiplied by cos theta, which is a, divided by a square root of a squared plus x squared. Oh, that might be, I might be in trouble here. But anyway, lambda dx 4 pi epsilon naught a squared plus x squared multiplied by a divided by square root of a squared plus x squared. I'm a bit of in a pickle because I'm not sure I know how to do this integral. Okay. Anyways, the total field, is the sum of the individual fields yi, which in this case is the integral from minus infinity to plus infinity of this monster, lambda a dx over 4 pi epsilon naught, and there we have a squared plus x squared to the power 3 over 2. Okay, I'll try to look up this integral. 1 over x squared plus a squared to the power 3, 2. Okay, while it's loading. Anyways, I might have made a mistake, but the idea is that you add up all the fields. So using the principle of superposition, this is the principle of superposition here, and the principle of superposition. You get this, and you should get um, once you do this integral. And this is going to be lambda over 2 pi epsilon naught a. Okay, this integral is doable. It's done by substitution. Oh, that's a complicated substitution. What's the result? Oh, that's nice. Okay, so the integral, we're going to use the integral. So with difficult integrals, sometimes it's just worth looking them up. So the integral of dx over a squared plus x squared to the power 3 over 2 is x over a squared multiplied by 1 over square root of a squared plus x squared. Okay, so using that integral, we're going to substitute that in. So it's going to be lambda a over 4 pi epsilon naught. So that doesn't change. This is a constant. Multiplied by this, by x over a squared, 1, well, we don't need that. So it's just x over a squared square root a squared plus x squared. And now we substitute from minus infinity to plus infinity. And to solve this, I'm going to do a trick here. So don't worry if you don't fully understand what I'm doing. This is like, I'm going to divide top and bottom by x. So divide, so that makes 1 over a squared square root a squared over x squared plus 1. So by dividing by x, what I did is I got 1 because I've put the x into the square root. And now I can safely substitute plus infinity and minus infinity. So plus infinity gives me 1. Okay, uh, there's a there's a modulus x here. Okay, there it's slightly more trickier than this. So I've taken, okay, almost that. I'm gonna take x of the square root, and it becomes modulus x is modulus x. So taking modulus x out, and then I have a squared over x squared plus 1. Okay, otherwise it just doesn't make any sense. Now I substitute plus infinity, and I get, so 4 pi epsilon naught, open bracket. I substitute plus infinity. This cancels. This becomes 1, so it's just 1 over a squared. Then I substitute minus infinity, and magically I get minus minus, and it becomes 1 over a squared. And then I get lambda a, 2 lambda a over 4 pi epsilon naught a squared. A cancels, 2 cancels, and I get lambda over 2 pi epsilon naught a. Ta-da. Yes, I got it. No mistakes. I did look up the integral though, so I cheated, but it's okay. You're never expected to know all the integrals. And it's impossible. It's impossible to know all the integrals in the world. Cool. So problem 3. Find the flux of an electric field created by a point charge through a surface on the sphere of radius r. So we're going to talk about flux, electric flux. The electric flux is defined as, so if you have an electric field, so flux, let's say you have an electric field, and this electric field passes through an area A. And let's consider that this is a small area. Let's call it, well, yeah, dA. So the flux flux is equal to the electric field times the area. But there's a caveat here. It's the electric field vector multiplied, it's the dot product of the electric field and the area. But you would ask me, Vlad, how could the area be a vector? Area is not a vector. But you can represent area as a vector. So A is a vector where the modulus of A is equal to the area, and the direction of A is normal to A, to the surface, to the surface, to the surface. And that becomes really useful. You just multiply it. You multiply the, yeah. In simple words, you could really understand it as, well, it's how much electric field is passing through an area. You can say how many field lines, right? Although you can't really count field lines, but that's the effect of it. So, um, sort of how many how many lines pass through a given area. Pass through a given area. You can think of it, I don't know, oh, the wind, yeah? So imagine you have the air moving. The air is moving, and you create a big loop. So the flux would be how much air is passing through your loop in a second. So flux, yeah, how much air, and like in here is how much of the electric field is passing through your loop. And yeah, so let's consider a point charge, and it produces a field around itself. And you want to know the flux passing through a sphere of radius r. Sphere of radius r. Well, you want to know the field. So we know that the strength of the field is equal to Q divided by 4 pi epsilon naught r squared. And we know that the area of the sphere, A is 4 pi r squared. So the flux, the total flux, would be E times A. Now, E is perpendicular to A. Sorry, E is in this, well, it's perpendicular to the surface. That means it's parallel to the normal vector of the area. So this is the normal vector. So they're parallel, so we don't need any angles here. So it's EA, and you just multiply them. So it's going to be Q over 4 pi epsilon naught r squared multiplied by 4 pi r squared. 4 pi r squared cancels, and you get Q over epsilon naught. And that's actually Gauss's law. Flux is Q over epsilon naught. Okay. Now consider this example. A cube is placed in a uniform electric field. Find the total flux through the faces of the cube. Well, it didn't specify. Let's cube 1 meter. 1 meter. 1 meter by 1 meter by 1 meter cube. So for simplicity, well, I didn't specify, but I'm going to use a field that is vertical. Okay. And you know what? I'm going to do the calculation. So I have 6 faces. So imagine the electric field is going from bottom to top. So the electric field, um, and it's a vector. So I'm going to write it as a vector. It's 0, 0, 20. Okay, because it's going up. It's along the z-axis. So this is the z-axis. This is the x-axis. And this is the y-axis. Now, I have 6 faces. So let's label them. 1. Oh, that's going to be annoying because how do I label them, making it clear which one's which? Um, so top. Yeah, let's call them top, bottom, left, right, front, back. Okay, this is back. Okay, so the front, this is the front. Okay, area of the top. Now, any surface, any flat surface has 2 normal vectors. One vector going outwards from the um, from inside the box, and one going inside the box. So we're going to use the outside vectors. So what does that mean? Well, it's going to be the normal vector will always be pointing outside the box. Okay, outside the box. Okay, so the top plane has a normal vector. Sorry, the top plane A. Oh, the top plane, it's a vector along the z-axis, and the modulus of that vector is the area. But the area is a 1 by 1 meter cube, so it's 1. So it's going to be 1. Oh, sorry, 0, 0, 1, because it's along the z-axis, and that's meters squared. And this is newtons per coulomb. A bottom. Sorry, I did not see that comment. Can you please write the comment again? It's very quickly disappears, and I don't know how to. I don't know how to get it back. Chat. Oh, does flux have unit? Yes, flux has unit. Um, we'll work that out. We'll work out the units for flux in a minute. So, well, it's obviously newtons per coulomb times meter squared, and we can simplify that. Does it have its own unit? I don't think it has its own unit. Yeah. So the bottom, the bottom plane, it's opposite to this. So it's going to be 0, 0, minus 1. And then the area of the left area vector is going to be facing left, so against the y-axis. So it's going to be 0, minus 1, 0 meters squared. And area right is going to be 0, 1, 0 meters squared. Area front, it's along the x-axis, so it's going to be 1, 0, 0 meters squared. And area of the back back face of the cube is going to be -100 meters squared. Okay, so now I want to find the flux through each of the faces. So the flux through the top face, now it's not a vector, it's the E times a top. So that's going to be 0, 0, 20 multiplied by 0, 0, 1. So that's going to be 20. Now it's newtons per coulomb meter squared. Newtons meter squared per coulomb. Can you simplify it? Well, Newton is kilogram meter squared per coulomb meter squared. So kilogram meter to the power 4, ampere minus 1, second minus 1. That is the base unit. This is in base unit. Flux, does flux have its own unit? No, I don't think so. Yeah. Well, it has units. You can express it in SI units. So I'm just going to leave it as newtons per coulomb meter squared. Okay. Now we know flux from the bottom, some face, is equal to 0, 0, 20 multiplied by 0, 0, minus 1. And it's going to be minus 20 newtons per coulomb meter squared. And this is a significant result here. We're taking a cube and the flux going in, sorry, the flux going out in this particular case, it has a positive sign, and the flux going in, you know what? That's what we have had to use. Yeah, to reverse. Let's reverse the normal. Let's make more sense. Reverse normal. The normal. So we're going the inside. Let's use the inside normal vector, and that becomes -1, +1, +1, -1, plus -1, +1. So the top is -20, and this is +20. So the flux going into the cube is positive, and the flux going out of the cube is negative. So yeah, going out and the flux going in. Now the flux through the left, as you could see quite easily, if you multiply the left by the E, it's going to be 0. It's going to be equal to the flux to the right, and is going to be equal to the flux front, and equal to the flux of the bottom. Oh, sorry, flux front, back. It's all going to be 0 because there's no flux, because the faces are parallel to the E. So there's no flux, and you can clearly see that from the multiplying the vectors. But the important thing is the flux going into a closed hollow shape is positive, and the flux going out is negative. And the total flux in this case is of course 0. The total flux going into the cube is 0. And that is and this is also an important consequence of Gauss's law. Gauss's law. Gauss's Gauss's law. If you have a closed surface, the total flux through any closed surface, total flux through any closed surface is Q inside divided by epsilon naught, where Q is the charge located inside the closed surface divided by epsilon naught, which is the which is a constant. And this law has very significant consequences. Now remember how we used this wire. We wanted to find the field around the wire. And we ended up having an integral which well, very few people can do off the top of their heads, basically. And yeah, but Gauss's law allows you to find this result in a much less painful way. So solve problem 2. Solve problem 2 using Gauss's law. Problem 2. Problem 2 using Gauss. Okay. You have an infinite wire which is charged. And let's take a cylinder around the wire. An imaginary cylinder around the wire. Now we already discussed how the horizontal components cancel out. So we know that the field at this point, which is a distance a away from the wire, is only going to be strictly vertical, the electric field. So we can find the total flux. So to find the total flux through the inside, the flux through the inside, it's simply the charge located on this line, and let's call this length L, and the charge is lambda L, and okay, and the flux is the E, electric field, multiplied by the area. And that means that electric field can be found as the flux divided by the area. And what is the area? Well, the area is the area of this cylinder. But you can see that we want to know area is the curved area of the cylinder is 2 pi a, which is the length, multiplied by L. That's the curved area. Now, this area is pi r squared, and this area is pi r squared. But we've already discussed, if you have a charge in the middle, and you have two faces placed symmetrically to one another, the flux in this direction and the flux in this direction. Oh, sorry. The flux through these faces would be zero because the field, we already know that the field is perpendicular to the wire. Yes. So the flux through the left and right. So flux to the left end is going to be zero because the field is perpendicular to the wire. We already know that. And the flux to the right is also zero. Okay, so there's no flux passing through the flat ends of the cylinder. So it's an imaginary cylinder, and the flat ends are placed parallel to the field, so there's no flux passing through them. So we only need the flux passing through this curved part of the cylinder. And that's it. That's what we sub in. From Gauss's law, is that the flux is the charge divided by epsilon naught, and we know the charge is lambda L divided by epsilon naught, and we just sub that into here. So electric field is the flux, so flux divided by A, which is lambda L divided by epsilon naught divided by area 2 pi a L. L cancels, and this is going to be lambda over 2 pi a epsilon naught. So compare this solution to this solution. The same problem, two different solutions. I'm actually very surprised that I managed to do problem 2 without mistakes, or at least I found the mistakes and solved them. But this is the power of the Gauss's law. It allows you to find fields from prolonged objects in such an easy way without like any complicated maths whatsoever. So absolutely genius law. And similar to that, you can find the field from an infinite plane of charge density sigma. I won't go through that. I don't have time. But there, I'll just give you the result. So I think it's there's a video link on sigma over 2 epsilon 0. So the field from an infinitely charged infinite plane, the field is sigma over 2 epsilon naught. Okay. Now where sigma is the charge density, so sigma is the charge per unit area, Okay. Problem 15. Find the electric field of an infinite charge slab with volume charge density as a function of Z. Well, this is one of the problems from the assignment. One of the important consequences of problem 4, which is above, is that the electric field from an infinite plate does not depend on the distance from the plate. Okay. So if you have a charged plate, it produces a uniform electric field, and any distance away from the plane, it would be the same. It would be the same same field, which is very nice. Find the electric field of an infinite charge slab. So if you are above the plate, then you just treat it. The field is going to be upwards, E. And that E is equal to sigma divided by 2 epsilon naught. What is sigma? Well, we need to work that out. Sigma is charge divided by area. But we know that the charge, because rho, charge density, rho is charge per volume. Therefore, here we can express charge as volume times rho. We sub that into here, volume, rho, area. What's the volume divided by area for a slab? Anyone? What would happen if you take the volume divided by the area? Make sense? H is volume over area. So it's rho H. So the field above the plate is rho H over 2 epsilon naught. Below the plate is the same, just in the opposite direction. Minus rho H over 2 epsilon naught. You can actually stop here, because if you are in the middle, you have charge above and charge below. They're actually proportional. So you can just draw the x-axis, so z-axis, z-axis. All right. So at 0, when z is 0, you are negative. It's going to be negative rho h over 2 epsilon naught. So now when you are at a height h, so this is 0, then it's going to be plus. So it's going to be like this. Rho h over 2 epsilon naught. And you can clearly, there's no reason why in the middle it's not going to be linear, because it's proportional to the widths. So in the middle, it's just going to go like this. So this is the solution. This is my gift to you. One of the problems solved, so that's E. But please do it, and yeah. Okay. I don't have time to do the next one, but I'll do some more graphs. So if you have a hollow sphere, okay, so if you have a hollow sphere, and this is an important result. So let's say this is X, and you have a hollow sphere, hollow sphere, and charge Q. And if you want to draw the electric field, so this is the radius of the sphere. This is the radius of the sphere. So outside the sphere, it will follow the inverse square law. It's going to be proportional to, well, it's going to be equal to Q over 4 pi epsilon naught r squared. But inside the sphere, the field is going to be 0. So the field inside a conducting, well, the field inside a hollow sphere is 0. And the field outside the sphere is the same as the field from a unit unit point charge. Now, if you take a solid sphere, which is charged, so it has to be a non-conducting sphere, because if it's a conducting sphere, all the charges would move to the edges, to the ends. But this is a solid sphere, and so the charges are located inside the sphere as well. So you would have outside, it's going to be a similar picture. It's going to be like this. So it's proportional to 1 over r squared. But inside, it's not going to be 0. It will linearly increase. And yeah. Something that you need to prove, actually, in your assignment. So you prove this by breaking it into smaller spheres. So when you are inside the sphere, you just imagine that you're on the surface of a smaller sphere, and you need to find the charge of the smaller sphere. But I have to go, unfortunately. And yeah, I really hope this was useful to you. And yeah, I'll see you next week for some maths. I have done more webinars on this topic, so please go back and see the previous webinars on electrostatics. Okay. So I'll see everyone next week.